Thank you everybody for coming. My name is Colin McCarthy. I'm a principal engineer. I'm originally from Dublin, Ireland, but I live in Seattle now. And I work on elastic load balancing. So elastic load balancing does exactly what the name sounds. We balance load. We take your incoming HTTP requests or TCP connections, and we balance them across EC2 instances. And I'm going to talk more about how ELB works under the hood, so to speak, today, and just dive a little bit more, in more detail around what's going on to help build applications on top of ELB and speak to its strengths. Okay, so I'm going to talk about three different parts of ELB. One second. Security, scalability, and availability, which we think of as the main features and the main reasons why customers are using ELB, and we'll go into some depth on each one. So we'll start with security. So what I want to emphasize in this section is, if you imagine ELB just like I described, as something that you run in front of your applications. So say if you've got a website or an API or some kind of service that you're running in the cloud, typically you'll have an elastic load balancer running in front of that. It is doing things like terminating your TLS SSL traffic or providing that first layer of defense. And what I want to emphasize is that everything I'm going to talk about in the security section is kind of independent of load balancing. And yet it's a big reason why we see people using ELB. We even have customers who put ELBs in front of just a single instance, just for the security features alone. So the first thing we do, like I said, is terminate SSLTLS, right? So if you create an elastic load balancer and you decide you want to terminate secure traffic on that, we support that. You can upload a certificate and a key, or we can generate them for you. I'll talk a little bit more about that in a second. And we handle keeping all of the SSL and TLS implementation up to date, and we try and make it easy to keep the configurations as up to date as possible. So examples of some of the things we've managed on behalf of customers are things like the SSL vulnerabilities that have been coming out over the last few years. We typically mitigate those on the same day or better. Some of them we managed to beat same day by having features disabled long before they're an issue. So Poodle, for example, the vulnerability in how SSL v3 can be used. We had same-day mitigation for that. Same-day mitigation for logjam, which is just to do with how Diffie-Hellman encryption is handled. We had same-day mitigation for Heartbleed, and the RC4 encryption cipher was removed long before that was considered insecure. And so the details of all those particular vulnerabilities don't really matter. But what I want to get across is, that TLS and SSL stack that we're managing at the front end, we're keeping all this stuff up to date. When these issues come out, if the most you might have to do is log into the console and update to the latest ELB security policy, and you're up to date with the latest settings. We always try to have those for same day. The way we're able to provide all that is, this is a space we are investing quite heavily in. We're trying to be quite deep when it comes to SSL and TLS processing, both for security reasons and performance reasons, to the point where we have our own implementation of the SSL TLS protocols. That's something that's open source. You can go view it on GitHub. It goes through regular, quite intensive security reviews and security audits. But that's something that's managed within the ELB team itself. So we're working on that code. We're constantly staying up to date. We're members of the SSL TLS community, so when security issues come around, we know about them. We're involved in mitigating them, and we can have all of those things prepared. So that's probably one of our biggest and simplest features. It's just that we terminate all that TLS SSL traffic, handle all of this stuff so that you don't have to, and can terminate the traffic in a secure, up-to-date way without having to worry so much about whether your own instances are up to date with the latest vulnerability of the moment. Recently, we added support for the AWS Certificate Manager to make this even easier. So now you can log into the console and create certificates through AWS. So you can go to the AWS Certificate Manager console, you can go to the ELB console or the CloudFront console, and there's APIs for all of this too. And you can create certificates using your own domain name. We'll send a verification email to the owner of that domain. Once they've verified that that certificate's okay, you can associate it with your ELB, and that's that. They're free, they're cost-free as well. So that's we're trying to make this as easy as possible to be able to terminate secure traffic. In terms of how we manage the SSL and TLS traffic, there's a few things going on under the hood. It can be quite confusing when you see the set of, what's a Cipher Suite, what are the policies meaning, and so on. Very briefly, what's going on under the hood is, well, what we try to present to you, very, very simple options. You can take the latest, greatest security policy and just use the default. But those policies are set up to prefer certain things. The first thing that we always try to prefer is what's called perfect forward secrecy. So that means when traffic is terminated on us, it goes through this extra algorithm called Diffie-Hellman. That means if the key were ever disclosed or compromised in some way, someone wouldn't be able to use that key to go back in time and decrypt a bunch of traffic that they had recorded. So it's a pretty awesome feature. We always try to use it. In terms of encryption algorithms, we always prefer to use AES. That's kind of our standard encryption algorithm over 3 DES, over RC4 if you have it enabled. It's actually disabled by default. There's these things called authentication algorithms, which are around how traffic can be made tamper-proof. We prefer the GCM algorithm over the CBC and HMAC algorithms. And when we're constructing these preferences, what we do behind the scenes is we construct this list of Cipher Suites in that order that we prefer, and then we test it against billions of connections from real-world clients. What we actually have is an experimental setup where we can send a very small amount of experimental Amazon traffic to these test endpoints where we will measure whether that Cipher Suite has any impact. And sometimes we find interesting things, right? Sometimes we find, that Cipher Suite in that order might impact certain versions of Java or, certain embedded system clients and so on. And so we're doing that kind of analysis on this list before we publish it to try to make sure that you can stay secure but also available, right? So that when we publish that update and you can choose the latest policy, that is not going to drop or break a bunch of traffic. And that's been working pretty well. We try to strike a balance with our defaults, right? We're always going to try to make sure that the Cipher Suites are secure, right? So the default Cipher Suite will try never to include something that's known to be insecure, and will minimize any gap of any systems that leaves unsupported. That can occasionally result in some systems, some very legacy embedded systems typically, that are so old or the software is not being updated that maybe they only support insecure Cipher Suites. We have a small number of customers who end up being impacted by this. Typically customers who are targeting things like set-top boxes and TVs and systems that aren't great at keeping software up to date, and maybe they got a version of software, when it shipped from a factory 5-6 years ago, and it's never been updated in the meantime. So a feature we added recently to try to help people manage this is to integrate all of this with our access logs. So access logs are another security feature that we have. I actually didn't really think of them as a security feature until I heard it from a lot of customers explain to me that they use our access logs in that way. But you can enable logging on your ELB, and we will record the details of each request, and we'll send it to an S3 bucket for analysis. And the reason that's a security feature is, in the AWS shared security model, we're responsible for the ELB. Right? We're responsible for the security of the ELB. It goes through a lot of rigorous review. We've got a lot of operational and security practices around elastic load balancers, making sure that they're not vulnerable and so on. And the same for S3. You can also protect S3 buckets with policies and so on. And so what you can do is, if you know that ELB is securely and reliably logging every request, well then if an attack happens to get through to your instance and say compromises some software vulnerability on your instance, like a WordPress vulnerability or something like that, typically a step an attacker might take is to erase all of the logs that are on that system itself. But if the ELB is logging and sending it off to S3, you've got this extra channel of log data that aren't as vulnerable to an attacker simply erasing things on the system and so on. We have partners that we integrate with if you want to do higher level analytics on that logging data. But going back to Cipher Suites, one of the more interesting things is we now log the actual Cipher Suite that was negotiated when a HTTP request came in. Right? So you can see this request, for example, used that Cipher Suite over the TLS 1.2 protocol. And that might be useful if you are, if you have a lot of legacy embedded system clients and you're worried about upgrading to the latest settings. Is that going to break something? Well, a simple way is to go through the logs and see is anything negotiating those. So for example, if you're upgrading to the latest policy and in the process disabling support for RC4, which you really should do, the RC4 encryption algorithm is definitely broken at this point. A good exercise to do might be to just enable logging, go through the logs, maybe a day or two's worth of logs, see if anybody's still negotiating RC4, dig into it, and see what's going on. When we were turning off RC4 for Amazon.com, one of the interesting things I learned was, well, we did this exercise. We went through logs, and we saw who was still negotiating RC4. At the beginning, we were kind of like, well, there's still some clients negotiating RC4. How are we going to turn this off? We don't want to break anybody in the process. And we actually found out a lot of the things still negotiating RC4 were, robots and spam bots and unwanted traffic in the beginning. So it was actually a positive to turn it off, which we only learned from scanning the logs line by line, which is pretty cool. So that pattern of using an ELB in front of your instances as kind of this known defensive layer that's kind of typically less vulnerable is an example of compartmentalization, which is another security pattern we see a lot of customers apply, where they'll launch ELBs into public subnets using VPC, that's our virtual private cloud for EC2, and they'll lock that down with security groups and IAMS policies and role accounts and so on, so that only trusted accounts with the right permissions can launch ELBs into that public subnet. That's the only way to effectively open a public port on the internet. And what that lets them do, is say, well, with some confidence, okay, the only things that have traffic coming in from the internet have these managed SSLTLS stacks that are being kept up to date. They have the certificates being managed by AWS. It can't simply be copied around or exported easily. And I've got logging in place so that any requests that come in are known. And that lets them open up and be a bit more free with what happens in the private subnets, because they can launch instances more freely there, be a bit more agile there, but know that it has to come through that top layer that's been set up a bit more. In addition to role accounts, we have full support for CloudTrail logging in the ELB API. So if somebody's creating ELBs, launching them into subnets, it's something that's completely known. And then we have access logging, which I already mentioned. In addition to all that, you can also enable VPC flow logging. So we also support that, which gives you additional logs that are network level. So you can see the actual sources and destinations of TCP traffic that are coming in and out of the ELB. So you can get quite a thorough, detailed view of everything that's going on and keep things nice and constrained. And all of that kind of feeds into standard threat models, helps you protect against some pretty common security threats. And so those are pretty popular features, and as I said, we see them even being used in some cases, even when there's just one instance behind that ELB, even when it's not doing any load balancing, just for the benefit of all those extra monitoring and kind of compliance features, which is kind of neat. Okay, but the real job of ELB is scaling, right? That's where things get a little more interesting. ELB at its root is a scalability feature. We're about taking, small or huge amounts of load in, whether it's from the internet or from, other EC2 instances, and spreading that load in a fair way and in a way that optimizes for your application. So I'm an engineer, actually, write code and work on ELB, and so I included an equation. I couldn't resist. And this equation is what's called Little's law, which I think of as one of the fundamental laws that applies to kind of balancing load or building systems, building distributed systems that handle many requests. And Little's law is simpler. It's pretty simple. All it says is that the total load or capacity of a system is equal to the rate of arrival, so that's lambda, times the average wait time, right? So the total amount of requests a system can sustain is just based on the rate they're coming in and how long it takes to process each request. Well, you can flip that on its head and say, well, the wait time is therefore equal to the capacity of the system, like how many instances you have or how much work your system can do, divided by the rate of arrival. Or in simpler words, latency is equal to load divided by throughput, right? So the more load you have in general, the more latent the system will be. It'll slow down a little. And the higher your throughput, the faster it'll get, right? So it's pretty intuitive. It's not a surprising result. But it has some interesting implications. So what drives the latency of modern systems, we always want to keep the latency low. People want their APIs to run quickly, or they want websites to load fast. People tend to notice things even in timescales of 100 milliseconds can be noticed by people. But a real challenge is that the kind of load or capacity of systems tends to be nonlinear, right? And there's a bunch of reasons why. One of the most common reasons is that a lot of applications use garbage collection, right? So what happens is, like if you start a backend in a garbage collected language, like say Java, typically it'll just build up memory and memory usage, until it hits some maximum heap size. And then the garbage collector will come in and it'll be busy doing its garbage collection. While it's doing garbage collection, it won't be able to process requests. And so latency will go way up when that garbage collection is happening. And on some systems, you can see really big deltas. You can see a system go from requests are taking 1 millisecond to, I've seen boxes take, tens of seconds to do garbage collection because they had heap sizes that were so large. The JVM was trying to free 10 gigs of memory all at once. So this box can go from being really quick to being really slow in an instant, right? So that's one common source of nonlinearity. Another common source of nonlinearity is caching, right? So at bottom, a lot of applications have caching at different layers, right? The common variables they're accessing, the common users they're accessing, or a shopping cart that's being edited right now might be hot in some cache, and one that was edited a few hours ago might be cool in some cache, right? And so a request that happens to hit warm entries in the cache will be really fast, because maybe that data is right there on the server handling the request. But you hit a cold entry in the cache, maybe it has to go to disk or some other box that's remote. And so you see the same kind of delta. And again, the difference can be huge, right? Something that's looking up local main memory can take microseconds. Something that's looking up, a remote distributed cache can take tens of milliseconds, right? So the several orders of magnitude difference. So there's a lot going on. And so what this tends to result in is kind of a very log normal distribution of request processing times, where you get, most of your requests, you're doing okay. They've got like some smallish processing time, but you get this tail of requests that are in the kind of higher percentile of your distribution that take quite a long amount of time, right? So you might have, an average request time of say 5 milliseconds, but then maybe your 99th percentile of requests might take like a second. That's not even that unusual. And so if we think about this as in terms of a queuing system, right? So servers and instances and even entire distributed systems can be modeled as queues. That's actually where Little's law comes from, is queuing theory. It kind of looks like, well, you've got a queue with small requests in it, and you've got queues with big requests in it, right? And this itself can be a source of variance in load, right? Like you might have a lot of small requests that are just requesting the front page, right? Those are probably hot in a cache. Those are probably easy to render. They're probably just a few K, right? But then occasionally there's a request floating around that's for, a big data dump, and the code has to go, dump a bunch of data from a database and process it and pivot it and do a bunch of things with it, and just takes a longer amount of time, right? And that feeds into the same pattern again, where your median request time is probably quite good, but your average request time's not going to be great. So, like, when we're trying to balance load, we got to ask ourselves, like, well, what can we do about this, right? What can we do to improve things? So the first thing we do is, well, we have more instances, right? We kind of throw more capacity at the problem. So instead of all of those requests contending on one instance and having to queue up linearly and just get processed one after another, we can throw several at it. And that can improve things, right? That can kind of smoothen out the tail. If even all you do is kind of like choose a machine at random, it'll tend to have some kind of smoothing effect where it'll kind of bring in the average, because on average, a box is probably free and it's not too busy. But your tail kind of stays where it is, because occasionally, bad request is still going to, a big request or a cache miss or a GC pause, if that's what we call garbage collection pauses when they slow the box down, can still occur at the same rate, and so the tail kind of stays where it is, right? So if we just separate the requests and we line them all up and we send them to different instances, we do get some benefit, right? Here I've got 4 instances. I'm splitting them up so that the queues are roughly equal in size. This is an example of something called round robin load balancing, where we just take a request at random and say, okay, well, you can go to this server, you can go to this server, and there's that will improve things quite a bit. It pulls in the tail, like I mentioned, but the real piece of magic that ELB does, which kind of blows my mind that it works so effectively, is we do something a little different, which is, so the previous queue kind of reminds me of a lot of queues like at a post office maybe, where everyone lines up and in front of their own server. But we try to queue more like a bank, where there's one line that everybody gets in, and then when a server is available, you go to the next available server, right? And this has the effect of saying, well, if you've got a box over here that's busy doing garbage collection, or it's got a cache miss, or is processing a big request, we're not going to send any new request to it while it's doing that. We're going to try to send it to one of the other servers, right? So this is called lease connections load balancing. Our implementation of it is actually a little bit more refined than that. We implement leased outstanding requests. So what we do is we count the number of requests that are outstanding to each of your instances, and we'll send the next request to whichever is the lowest, right? So if you've got capacity free in the system, that's where the next request is going, right? It's really, really cool. It's amazingly effective. Kind of blows my mind how effective it is. It's particularly effective when you've got a small number of slow instances, right? So if you've got a handful, like 2, 4, even 10 instances that are running a reasonably slow application, this will smoothen out those peaks, help quite a bit. It can really pull in the tail quite a lot, really flatten the load. And you're only ever going to see that tail when in general, the whole system is out of capacity, right? As long as there's capacity available somewhere, that's where ELB is going to try to route the request to. Surprisingly effective and amazingly cool. The one big downside of this, though, this doesn't all come for free, right? There's a little bit of a gotcha, is if you have a server that's being particularly fast, right, but it's actually not doing anything useful, like maybe it's just throwing 500 errors or exceptions or PHP crashes, that server is going to suck all the load, right? You're going to black hole traffic. So it's kind of a double-edged sword. It's really awesome algorithm in general when everything's going well. It's amazing at smoothing out differences in load. Does a really, really great job. But if you've got a box that's kind of poisonous and is kind of throwing errors quickly, it will rapidly suck in everything. So, it's pretty important to pay attention to boxes that are spinning like that and take them out of service quickly. But one simple trick you can also do is if you do have an exception handler or some kind of code path that's responsible for throwing those 500s, just put a sleep in there, right? Just slow it down so that it can only respond with 500 errors, say once every 200 milliseconds or something appropriately slow, so that box isn't just going to soak up traffic. If you want a bit of defense in depth, right? So that's the other side of all that. Now, all this only works, right, if ELB itself can actually take all your requests in at a faster rate than you could, right? It has to take the requests in, queue them up, and know where to serve them with very low latency and without throwing away any of those requests. So ELB itself has to be able to scale quite large and quite quickly. So to give you an idea of the kind of scales we run, we have ELBs today in production that run everything from literally, I've seen ELBs that handle literally 1 or 2 requests per day, but it was a very important workload and needed something in front of it just to trigger off a very important batch job and make sure there was some availability and resilience in place, all the way up to millions of requests per second, right? So it can go as high as your needs. So far, we've never hit any ceiling or limit we weren't able to scale up to. Our own scaling is a mix of kind of proactive scaling. So what I mean by that is if you add backends, if you add instances to your ELB, we scale up assuming you added those instances for some reason, right? So when you go add a bunch of instances, we will scale up to match that. And both then and in general, we're always very aggressive to scale up. So we scale up in minutes or less, and we're very cautious to scale down. So when you add those instances, we'll scale up, and we'll stay scaled up for quite a long time, like days, even if we don't see traffic. And after that, we go into our more reactive mode, which is we pay attention to the traffic patterns as we see them come in, and we scale ahead of that, right? So that's a reactive scaling. And there's a few things going on there to make sure that we're always at a higher scale than your own instance capacity. The first I already mentioned, it's quite quick, so we scale up in minutes or less. The second, I'll talk a little bit about when we get to availability, is we're always prepared for the loss of a data center. So every ELB is kind of typically overscaled by 50% or so. So there's this kind of buffer that's in there that's actually for disaster recovery in case a data center fails, but also means you've got this, huge margin you would have to run right through before you hit the ceiling. And then the other thing we do is it's predictive load balancing. So it's actually or predictive scaling rather. So we're looking at the load pattern and seeing where it's going to go and seeing what we need to do before you need it. So that's what we're doing for our own scaling under the hood. We provide a bunch of CloudWatch metrics. I'll go through them in detail in a bit, but it's also common to see people, use their load balancer as a kind of convenient way to manage their own scaling. So all of the CloudWatch metrics that we support can be used to trigger auto-scaling events in your own instances, right? And that's convenient because we have metrics like how many HTTP requests you're getting. And often you'll want to scale your instances based on that, but maybe not go through all the effort of building your own metric of how many HTTP requests you're seeing on the back end. You can just get it conveniently from the ELB. So you can match the scaling, right, of both the elastic load balancer kind of at the top or in front and your instances which are at the back. And they can stay in harmony, which is pretty cool. We provide 13 of those CloudWatch metrics, each of which can be used for scaling. Some of them don't make sense to use for scaling, like healthy host count and so on. But they're all possible to use for that. You can configure CloudWatch alarms on each of these metrics. You can get notifications when they go above those alarm levels. They're all provided at 1 minute granularity and so on. You can view them in the CloudWatch consoles. So having an ELB in front of your instances also gives you all that neat visibility into your traffic patterns in pretty close to real time. Minutes with about a minute's delay or so. Some of them are worth diving into. The healthy house count metric that's where we expose, this is kind of ELB's view of your instance health. So if you've got a number of instances registered behind an ELB, we give you a metric that tells you how many we think are actually healthy and in service. You can view it at an availability zone level. You can see how healthy we think your application is. ELBs are constantly health checking your instances so that we don't send traffic to an instance that's down. And so you can use this metric to trigger an alarm, replace that instance if you want to, do all those kind of neat things. If you're interested in measuring the performance, we have measurements for latency. So we'll expose the end-to-end latency. This is how long the whole request took, including the time it took ELB to process it and the time it took your instance to process it and so on. And you can see if your overall system is getting slower or if there's any kind of problem going on, it'll often show up as a latency thing. We have surge queue and spillover metrics. Surge queues are just these queues we keep on the ELB of requests that your backends can't accept yet. So if your backends get clogged up and aren't accepting requests, you'll see the surge queue start to fill up. That's something you might want to scale up on, something you might want to go tune or optimize an application for, or just add more instances if it's something you're managing manually and so on. We queue up to about just over 1,000 requests. After that, we found out through working with customers that it's better to start returning errors and kind of cause traffic to go away rather than simply backing up requests indefinitely, because what happens is the clients tend to time out, and so we're just queuing up all these requests, but there's no client interested in it anymore. And in some kind of overload event, it really harms the application's ability to recover. If it slows down and all that happens is these requests keep coming. So it's this queue size. This is designed to balance, giving you enough swash to kind of get around some kind of temporary clog or just short-term issue where your instances maybe aren't keeping up. It'll just help you out for a few seconds, but it's not going to queue things for so long that the system won't recover because we just keep hammering it with this stampede of requests. So it's quite interesting. When we do get to returning errors, that's spilling over. Those are spillovers, and we have a metric for those too. And so you can see if we get all the way to that state, that's what's going on. In addition to the metrics, we have the access logs that we saw earlier. Apart from the SSL and TLS protocol version, which we already went through on the Cipher Suite, we have all these fields too. So it's quite a detailed take on just what's going through your load. You've got all the different sizes, the size of the request, the size of the response, things like the user agent header, which can be really good for figuring out rogue clients, timestamps, and just a lot of fields that we found through experience tend to be useful. It's a bit more verbose than your typical Apache log, and that's just because we found cases where each of these are useful. In addition to all this scalability, which happens within a region, we also support global scalability with Route 53. So you can create a DNS domain name on Route 53, and you can route traffic using either latency-based routing, geo-based routing, or traffic policies, which recently launched, that let you send traffic from all over the world to different ELBs in different AWS regions. We have customers, particularly in very latency-sensitive businesses like advertising, that will generally run in what's called active-active modes, where they'll always try to send requests to the closest region. And we have customers who use this for failover between regions. So they'll have a primary stack in one region and a secondary stack in a whole separate region, and they will be able to fail over between them using DNS. And that's all supported with ELB integration. Route 53 knows about the same health checks that ELBs are making. So not only does failover happen if there were some kind of power issue or a data center failure or some major internet traffic event that meant traffic wasn't reaching a certain region. So it'll certainly fail over in those cases. But it will also fail over in the cases where your application in that region is the problem, right? So maybe your application has fallen over, it's failing its ELB health checks. ELB will actually tell Route 53, and Route 53 will be able to fail over. So we see some customers use it to manage blue-green deployment patterns, just like that. And that's kind of a good place to tee up our availability strategy and what's going on, right? How do we keep ELB highly available? And a lot of the patterns that we're doing here are things you can replicate for yourself, for your own instances directly too. So the first kind of availability feature that ELB offers is quite a simple one, which is, well, when you've got an ELB in front of your workload, right, you can replace instances seamlessly, right? You call the ELB API and you remove the instance, or you add a new one, whichever order you want. And as long as there's instances that are up and running available behind that ELB, we're not going to drop requests. In fact, ELB will actually, when you disassociate an instance from an elastic load balancer, we'll stop sending new requests to it, straight away. That's the first thing that happens. But we can drain traffic to the existing instance, right? So ELB will keep those connections open. It'll let that traffic drain, and then when it's gone, it's gone. You can turn off the instance, right? So you don't have to worry about doing very basic DNS tricks or problems that you might see with other load balancers where the second you take it out, it kills a bunch of connections that are in flight. So that's the first thing that's going on, right? That's all based on health checks. So we're always actively health checking every single instance that's behind that ELB. So another way to fail, or another way to replace instances, is you could decide to fail its health check, right? So if an instance crashes, we're not going to be able to reach it anymore. If your application crashes, we're not going to be able to health check it anymore. It'll be marked as unhealthy. We'll stop routing traffic there. But you could also decide to do it intentionally. It's just another way you could decide to take out instances. Sometimes people prefer that pattern because they've got DevOps processes where they can conveniently run code on that box. And so if you can cause the health check URL to fail, we'll also stop sending that box new traffic. But any existing connections that were open, we'll try to keep them going. We support a bunch of health checks like that. We do basic TCP ones and HTTP ones and HTTPS ones. You can customize the frequency and failure thresholds. It's something we're thinking about is, how deep do you want that health check to go? So we'll health check a URL of your choice, right? You tell us the URL, that's what we'll try to hit. Behind that URL, you can have a simple static response that just returns 200 and basically says, network connectivity to the instance works. That's a fine health check. But you could also decide, no, when I get that health check ping, I'm going to check that my database is alive. I'm going to try to do a SQL query, and only if I get a successful SQL query am I going to return 200, right? So you can go as deep as you like. And there's trade-offs in that. Sometimes if you go too deep, maybe you're just exercising the whole system too much and it's too costly. And sometimes if you go too shallow, if a dependency falls over and your application is down, but that health status is still 200, you're going to end up blackholing traffic, which isn't optimal. We also support idle timeouts. So in general, we try to keep connections alive, where we can, just to save some latency. You can configure those. You can set up how long you'd like them to be. The default is a minute, right? So we'll try to keep a connection over for a minute. So if your website's getting, or your application's getting more than one request a minute per, backend instance, in general, those connections will be kept open. But you can extend that as you like. But one thing to keep track of, right? One kind of gotcha with those idle timeouts, an important kind of detail, is, as I said earlier with the queues, there's no point queuing up work when a client gives up on it, right? If the client has its own timeout value, so let's say it's a browser, right? Typical browser timeout might be 30 seconds. Well, there's really no point having more than 30-second idle timeout on your load balancer. And if you've got a tree, if you've got a tree of applications where each one is calling another application and each application is behind its own load balancer, you probably want those timeouts to decrease as you get deeper and deeper in the tree, just to avoid doing work kind of deep in that tree at the edge of the system when clients have long ago given up on it. So that can be pretty important for maintaining your own availability, because otherwise what can happen is big workloads come along, the system gets a little slower because of Little's law that we saw earlier. Requests start to time out on the client side, but the servers are still busy doing work because the idle timeouts are too high, and it ends up making it harder for everything to recover. So that's a pattern worth applying if you can. So I hinted at earlier with our own availability, but what we're doing, right, for ELB's availability is that an elastic load balancer is provisioned in multiple availability zones, just like your instances are, hopefully, if you're running some kind of high availability setup. And all that's happening, all that we're doing, to make sure that your ELB is up and available and in service at all times is we run Amazon Route 53 health checks. So every ELB is hosted on Route 53, and there's a bunch of IP addresses associated with that ELB. Some of them are in, Zone A, some of them are in Zone B or C or D, and so on. And if you do a DNS lookup on ELB, you'll get back an answer set that has a mix of IPs from each availability zone that's up. But we've pre-configured a set of Route 53 health checks that are happening, all the time from, I think, 16 locations all over the world that are constantly health checking those ELBs and making sure that they're up and available. And if any of those IPs are unreachable, Route 53 withdraws them from DNS. And on the ELB side, we don't do anything else in general, right? We let Route 53 withdraw those nodes from service. Traffic will stop coming into them, and traffic will keep going to the ones that are up and available. And if it's some kind of power event, hopefully when power is restored, everything's back to normal. If it's some kind of network event, like a big kind of internet transit issue and so on, when that's passed, everything goes back to normal. But there's not a lot of work going on behind the scenes. And that's kind of a key to our availability strategy, where when we have these large events, when big things are happening, we don't try to do more work, right? We don't try to have APIs and systems behind the scenes that are scrambling to, remove this, add this, remove this, add this. Because what happens is that tends to make things worse, right? The system's already overloaded, so adding more change to the system can make things worse. Instead, we try to do a constant amount of work. So those Route 53 health checks, they're just always happening all the time, the same rate. When something's up, when something's down, all that really happens is something flips from healthy to unhealthy, and DNS is in or out. So it's kept extremely dumb, extremely simple, and therefore very reliable in our experience. This has weathered, several large, internet transit events, for example, quite reliably. And one of the really nice properties of Route 53 health checks is because they come from all over the world. Sometimes you'll get a different view in one part of the world than you will other parts, right? Because maybe the network has a problem from that side, but not others. This all works because we're in multiple availability zones to start with. We always try to match elastic load balancer so that our nodes are in the same availability zone as your nodes. And we support cross-zone load balancing as well. So when we match the zone that your instances are in, right, traffic will come to the ELB that's in a certain zone. If we keep traffic in that zone, what can happen is there can be an imbalance in the traffic between the two zones, because the kinds of load balancing that DNS can do, which is how we route traffic to zones, isn't as good as the kind of load balancing we saw that ELB can do. So one simple thing, one simple tip that we advise people on is to use cross-zone load balancing, which is now the default, but on some load balancers may not be enabled. And that'll smoothen all that out. So what'll happen is ELB will soak up any imbalance that comes in between the two availability zones because of DNS load balancing, and we'll just even it out. We'll just send the traffic to the least loaded instance, like I said. So for all that to work, when you create your elastic load balancer, if you're using VPC, we ask you to associate 2 or more subnets, one in each availability zone, with the elastic load balancer, just so that we can provision those nodes. And here are those traffic imbalances I was talking about, right? So if you've got a relatively small amount of load, if you're in a large amount of requests, things will just even out. Even DNS can even that out because the laws of large numbers will take over. But if you've got a relatively small number of requests, then occasionally DNS can send 50% more traffic to one zone than another. That's in effect because of DNS caching. What happens is if all your customers are on, a small number of networks with a small number of DNS providers, we see this with, iPhone apps, for example, because all of the users are all on a few cellular networks, and those cellular networks only have a handful of DNS servers. That means there's only a few DNS answers in play at any given time, right? So, occasionally, the dice can just roll such that those DNS servers all send a bit more traffic to one availability zone than another. We do have a suggested workaround for this. If you really want to get very even DNS load balancing, that's to create a wildcard name that maps to your ELB, and in your application to make up a nonce or a UID or some kind of field that you're never going to reuse, so we'll always bust a cache, we'll always get a unique response, and put that in your application, and that'll even things out. But alternatively, you can just enable cross-zone load balancing and let ELB figure it out, right? So that's the same zone load balancing that I mentioned. That's the cross-zone load balancing. And then we've got a graph evening it out. Sorry about the slides not advancing, so we're going a little out of order. Great. So the last thing I want to mention is that everything I've talked about here, everything that I've covered in ELB, it's all scriptable. We've got APIs for everything. We integrate with all of the AWS kind of managed DevOps offerings, and plenty of third parties are using it too. Increasingly, we're seeing folks use ELBs as kind of deployment aids, where people will create a whole new stack for a new deployment with a new ELB in front of it, test their workload through the ELB, and then flip the load when they're done. So you're going to see us have features that really enable that use case, make things even easier for folks that are doing those kind of workloads. But that's it. That's everything I have. Thank you all for coming. If you have any questions or any more detail I can fill you in on, just feel free to ask me. I'll be right down here after the talk, and then maybe outside if they kick us out. Thank you.